Hello, I'm Seema and welcome to part 17 of the chapter Periodic Classification of Elements. In this video, I'm going to discuss the periodicity in chemical properties, and we're going to focus on the periodicity of valence or oxidation states. What is valence? Valence is the combining capacity of an atom. It means I told you about the octet rule, that all elements are in a race and they are trying to acquire the octet, which is the noble gas configuration. That is 8 electrons in their outermost shell. If they have less than, and an atom cannot have more than 8 electrons in its outermost shell. So if they have electrons which are less than 8, then they have two choices. Either they lose electrons and acquire the octet of the previous noble gas, or they gain electrons and they acquire the configuration of the next noble gas. And there's a third option that they have, that they combine with each other and they share certain pairs of electrons in order to acquire the octet. And the shared number of electrons would also be counted as electrons of both the atoms, and hence they would contribute to completing the octet of both the atoms. Well, that having been said, let us see what this combining capacity is in the periodic table. If you see the number of the group, that is, I'm now talking of the representative elements. In representative elements, we have group 1, group 2, and group 13 to 18. These are elements in which the electron is being added in the outermost shell. In group 1, there is only 1 electron in the outermost shell. In group 2, there are 2 electrons. In group 13, there are 2 electrons in the s orbital and 1 electron in the p orbital. So there are 3 electrons in the outermost shell, 2 electrons in the p orbital. So in the outermost shell, 2 electrons in the s orbitals and 2 electrons in the p orbitals. So these are the number of valence electrons, that is the number of electrons in the outermost shell of a group. For group 1 it is 1, 2 is 2, 13 is 3, 14 is 4, 15 is 5, 16 is 6, 17 is 7 and 18 is 8. These are the number of electrons that are present in the outermost shell. Now, in order to react to acquire the octet, the elements, they either lose, gain or share electrons. And what is this number? How do you calculate it? That number is called the valence. And valence is calculated, or it is rather either the number of electrons in the outermost shell, or it is 8 minus the number of electrons in the valence shell. We call these, the number of electrons in the valence shell are called valence electrons. So for group 1, the valency should be 1. For group 2, the number of valence electrons is 2, so valency should be 2. For 3, it's 3. For 4, it's 4. And for 5, it is either 3 or 5. For 16, it is either 2 or 6. And for 17, it is either 1 or 7. And for 18, it is 0 or 8. Now the question is, I said that the way to calculate the valence is, it is either the number of electrons in the outermost shell, or it is 8 minus that number. Then why do we not have those numbers here? When you are calculating or finding out the valency, it usually is for 1, 2 or 3, they would like to, these atoms would prefer to lose electrons, 1, 2 or 3 electrons, in order to acquire the octet of the previous noble gas. 4 electrons, they can, I told you, losing or gaining 1 electron requires energy, 2 more energy, 3 even more energy, and 4 is impossible. Therefore, the elements in the 14th group, they do not lose or gain electrons, they prefer to share electrons. And hence, 4, they show a valency of 4, and 8 minus 4 would also be 4, so they have only a valency of 4. But when you come to group 15, which have 5 electrons in their outermost shell, they either gain 3 or they share 5. They either gain 3 or they show variable valency of 3 and 5. And group 16 would show a valencies of 2 and 6, and group 17 would show valencies of 1 and 7, although the lower number is always the preferred reaction. That would be the preferred valency. So group 15 elements would prefer to lose 3 electrons or share 3 electrons. And group 16 would prefer to lose or share 2 electrons, and group 17 would prefer to show a valency of 1 instead of 7. Because if you can clear an exam by appearing for only 3 tests, and you have a choice of appearing either for 3 tests or 5 tests, you would choose to appear for 3 tests. Lesser work is always easier. And here, you either appear for 7 exams or just 1 exam. You would choose the 1 exam. So, the effort that you would like to put in is always less. Therefore, losing, gaining or sharing of 1, 2 and 3 electrons would be preferred in comparison to the other valencies. But the other valencies are also shown by these elements. And there are reasons for that we'll study later. So this was valency. Valency is the combining capacity of atoms. It is the number of electrons in the outermost shell, or it is 8 minus that number. Now these days, instead of valency, we prefer to use the term oxidation state or oxidation number. What's the reason for using this term is that whenever we have covalently bound atoms, one of the atoms, if there are 2 elements, would be more electronegative in comparison to the other. So even if it is a covalent bond, one of the atoms has a tendency to pull the shared pair of electrons towards itself, thereby rendering it a little bit of ionic character, a little bit of charge. It may be very little, but still there is a charge. So to bring this charge into consideration, or to keep the electronegativities into mind, we use the term oxidation states. When do oxidation states become really significant? When you have elements like, let us see this one example. Oxygen combines with fluorine to form OF2, and oxygen also combines with sodium to form Na2O. Now what is the difference in these? When oxygen, out of these 3 elements, that is fluorine, oxygen and sodium, let us write down the electronic configurations. Oxygen is the 8th element, fluorine is the 9th element. So 9th element would be 1s2, fluorine configuration would be 1s2, 2s2 and 2p5 is fluorine. Oxygen is 1s2, 2s2, 2p4, and sodium is 1s2, 2s2, 2p6 and 3s1. So what do we see in sodium, oxygen and fluorine? Fluorine is a halogen. It has 7 electrons in its outermost shell. Oxygen has 6 electrons in its outermost shell. And sodium has 1 electron in its outermost shell. In order to acquire the octet, sodium should lose 1 electron. In order to acquire the octet, oxygen should gain 2 electrons, or it should share 2 electrons. Because it has 6 electrons, to complete 8, it should either gain or share 2 electrons. Fluorine, on the other hand, has 7 electrons in the outermost shell. It needs only 1 electron to complete the octet. So it either gains or it shares whatever is available. So out of these, which ones do you think are most electron deficient? That is, which is the, I wouldn't say electron deficient, which is the element which would be most electronegative? In the previous video, I told you that fluorine is the most electronegative in the entire periodic table. So it has a tendency to always pull a shared pair of electrons towards itself. Oxygen is also electronegative, but fluorine is even more electronegative than oxygen. And sodium is a metal. It is a king. It gives out electrons. So it is electropositive in nature. It has a tendency to give away its electron. So if we just write them in sequence of their electronegativities, the electronegativity of fluorine is the highest and that of sodium is the least. So when oxygen combines with these 2 elements, it behaves differently. It appears to have a different charge. With sodium, oxygen behaves as a negative, appears to have a negative charge. It actually has a negative charge because this is an ionic compound. Sodium has 1 electron and oxygen needs 2 electrons. So 2 sodiums give 1 electron each to one oxygen atom, and therefore the formula of sodium oxide is Na2O. Oxygen needs 2, sodium gives 1. So you need 2 sodiums to give the 2 electrons to oxygen. And in this case, the the charge of oxygen is 2 negative. Right? The oxidation state of oxygen in this compound is 2 negative. In OF2, on the other hand, fluorine is more electronegative. It tends to pull the electrons towards itself. Fluorine needs only 1 electron to complete its octet, but oxygen needs 2. But since fluorine is more electronegative, 1 oxygen gives 2 electrons to 2 fluorines. Do you see? So the oxygen here, although it is giving, they are sharing the 2 electrons, here its apparent charge is 2 positive. It appears to be giving electrons to the 2 fluorine atoms. So although it is not an ionic bond, it is not actually transferring the electrons, but yet the apparent charge on oxygen here is 2 positive. So the oxidation, we call this, the apparent charge is known as the oxidation state. So oxidation states are used more in comparison to valence these days because the oxidation state tells you about the comparative electronegativity difference between the 2 elements which are combined together. And when it combines with that, in comparison to that other element, is this element positive or negative? And the valence, that is the number of charges that it is showing, is that charge positive or negative? So that was oxidation states. So we have seen in the group, the valency or the oxidation state usually remains the same. All elements of a group show the same valency or oxidation state. But as we move from left to right, in the periodic table, the valency first increases from 1 to 4 and then seems to decrease from 4 to 0 in noble gases. Noble gases would show a valency of 0, 2. So that is the periodic trend. So the formulae of hydrides have been given here for elements of different groups. The first group elements have a valency of 1. That means an involvement of 1 electron. And hydrogen also is in the first group. It also has 1 electron in its outermost shell. And it has a combining capacity of 1. So since hydrogen has a valency of 1, whatever it is combining with, that can give us an idea of the valency of that other element. Lithium hydride has a formula of LiH. We know hydrogen has a valency of 1. The number of electrons transferred, lost or gained should always be equal for both the atoms. Whatever is the exchange, whether it was a transfer of electron or it was a sharing of electron, the number of electrons involved should remain fixed and should be the same for both the elements. So 1 electron here, 1 lithium, it means lithium has a valency of 1. Sodium also 1, potassium, all elements would have the same formula of the hydrides. Calcium has 2 electrons in its outermost shell and hydrogen has a valency of 1. So calcium gives 2 electrons and if it gives 2 electrons but hydrogen needs only 1 electron. So 2 hydrogens accept those 2 electrons. 1 hydrogen accepts 1 electron and the other hydrogen accepts 1 electron. Thus the formula of calcium hydride becomes CaH2. In the 13th group, we have 3 electrons in the outermost shell. So boron forms the hydride B2H6. The formula is B2H6. H6 means that there are 6 electrons in the case of hydrogen. Alright, because every hydrogen contributes 1 electron. So there are 6 electrons. If there are 6 electrons of hydrogen, how many borons do we have? 2. So these 6 electrons are being divided by 2 borons. So how much is each boron getting? 3. So what is the valency of boron here? 3. Aluminium hydride is AlH3. 1 aluminum and 3 hydrogens. It means the valency of aluminum will be 3. Then we come to the 14th group. They have 4 electrons in the outermost shell. Carbon forms CH4. Which means that if there are 4 hydrogens and 1 carbon, the 4 hydrogens means 4 electrons. So carbon should have a valency of 4. It's the same with silicon, germanium and tin. Right? All of them form hydrides which are H4s. Then we come to the 15th group. 15th group also shows a valency of 3 with hydrides. See, nitrogen H3, NH3. If there are 3 hydrogens, there's an involvement of 3 electrons and these 3 electrons are being given to the nitrogen. So nitrogen requires 3 electrons, so it is showing a valency of 3. Come to the 16th group now. There are 6 electrons in the outermost shell. And the hydrides, what are the formulae? H2. Now do you see here, when you come to the 16th group, we were writing hydrogen later. Here we are writing hydrogen before the element. It means when it comes here, the hydrogen becomes electropositive in comparison to these elements. So in the formula, it comes before. We usually write the electropositive element first and the electronegative element later. We'll do details of this later, but let us just focus on the valencies. Now hydrogen, there are 2 hydrogens and 1 oxygen. Oxygen needs 2 electrons and those 2 electrons are being shared with 2 hydrogens. So 1 electron going to, because hydrogen has actually a capacity of only 1. So if there are 2, it means that valency is of oxygen, sulfur, selenium, tellurium. And with fluorine, we have HF, HCl, which means here the halogens are displaying a valency of 1 in all these hydrides. Let us now move to the oxides and see how their formulae are. Oxygen has 6 electrons in its outermost shell. It belongs to the 16th group. So it has 6 electrons, which means its capacity, combining capacity or valency is 2. It needs 2 electrons to complete its octet. So when oxides are formed, what would their formulae be? Now we have to keep in mind that oxygen always has the valency of 2 in all these compounds. So based on that, we'll calculate the valencies of the other element. Oxygen is 2 and lithium are 2. And we know group 1 has a valency of 1. So if it has a valency of 1, oxygen has 2. So obviously the 2 electrons are being gained from 2 lithiums. Whether it's covalent or the oxidation state is 2 negative of oxygen. So lithium would be 2, is actually 1 positive. But you needed 2 lithiums because the 2 lithiums are going to contribute the 2 electrons required by oxygen. Similarly, sodium, there are 2 sodiums. The 2 sodiums will give 1 electron each to the oxygen to satisfy the requirement of 2 electrons of oxygen. Potassium again, 2 potassiums will give the 2 electrons. In the case of the second group, magnesium, calcium, strontium, barium, they need to lose 2 electrons and oxygen needs to gain 2 electrons to acquire the octet. Simple exchange, 1:1 ratio, one magnesium will give 2 electrons to the oxygen and therefore the formula is MgO. Group 13, how do they form their oxides? Every oxygen needs 2 electrons, but the 13th group element has a capacity of 3. So when you have 2 and 3, what will we do? The 1 oxygen needs only 2 electrons, but 1 boron is going to give 3 electrons. So if it has to give 3 electrons, it cannot give 3 electrons because oxygen needs 2. That's an even number. So it will have to donate in the same number. So what we do? Interchange the numbers. Boron, if you have 3 oxygens, it means 3 oxygens will gain how many electrons? 6 electrons. So 1 boron gives 3 electrons. So how many borons would you need to satisfy the 6 electrons? 2 borons, therefore the formula is B2O3. Similarly with aluminium, gallium, indium, Al2O3, Ga2O3, In2O3. Now come to the 14th group. Every oxygen needs 2 electrons, but the 14th group elements have a combining valency of 4. So you will need 2 oxygen atoms to satisfy that valency. And the formula is CO2, SiO2, GeO2 and so on. When you come to the 15th group now you see the 15th group usually shows both the valencies 3 and 5 when it combines with oxygen. Although when it combined with hydrogen, it only showed the lower valency, but with oxygen, it is showing both the valencies. N2O3. In N2O3, 3 oxygens means 6 electrons, and 6 electrons are being divided by 2 nitrogens, which means 1 nitrogen gets 3 electrons. So what is the valency of nitrogen in N2O3? It is 3. But in N2O5, O5 means there are 10 electrons being divided by the two, or distributed between the two nitrogens. So 5 divided by 2 would be 5. So in this, nitrogen is showing, in N2O5, nitrogen shows a valency of 5, while in N2O3, nitrogen shows a valency of 3, while the valency of oxygen is fixed, which is 2. It's the same with the other elements of this group. When it combines with 16th group, both oxygen and the 16th group element, they require 2 electrons each. And they do require 2 electrons each, but the electronegativity of oxygen is more. And when it combines with the elements of this group, the lower elements of this group, it tends to have those elements tend to have a valency of 6. So the oxides which are formed with these elements is sulfur trioxide. 3 oxygens, which means the valency 6 electrons, and who is giving the 6 electrons? Sulfur. So the sulfur here is displaying a valency of 6, although with hydrogen it was displaying a valency of 2. Similarly here in the case of halogen, Cl2O7, 7 oxygens means 14 electrons, and these 14 electrons are being contributed by 2 chlorine atoms, which means one chlorine atom gets 7 electrons. So what is the valency combining capacity? 7. So this was just a little idea of how we get the formulae using the valencies, and how there is a periodicity, there is a trend in the formulae of the compounds that these elements form. Because basically the chemical properties depend on the electronic configuration. So it is the configuration which decides all the chemical properties. And that is why the properties of elements which have similar electronic configuration and the compounds they form have the similar formulae too. Interesting, isn't it? So as we move on with our chapters and we study these different blocks and groups separately, we'll do more and more chemical properties in details. But right now we'll just be doing this and study just a little bit more in 1 or 2 more videos, and then we'll move ahead with the next topic. Thank you for watching. If the video helped you, please like it and subscribe to my channel and recommend it to your friends. And please keep returning for more videos in chemistry. Bye-bye.